When you tap Place Order on a food delivery app, your device initiates a massive, high-speed exchange of data packets across a digital mesh. Modern applications no longer run as giant single blocks of code. They are split into distinct microservices, individual backend nodes, where one server handles user accounts, another processes payments, and a third tracks restaurant inventory. This diagram shows the resulting network structure. When a client device connects directly to each distinct microservice it needs, the architecture degrades into a chaotic web of overlapping connections. This decentralization forces developers to duplicate critical operational logic. They have to code authentication checks, rate limits, and security protocols into every single backend node individually. Decentralized routing creates an unscalable network. The client app is forced to hold the map to the entire backend ecosystem, and the servers burn compute power managing redundant security checks. We resolve this by wiping the map clean and dropping an API gateway right in the center. The gateway acts as a reverse proxy, a centralized hub where the client sends one request and the gateway neatly fans out the traffic to the appropriate microservices. By centralizing the traffic, all those redundant security and authentication checks migrate off the backend nodes. They consolidate into a single, robust perimeter defense on the gateway itself. The gateway is an active orchestration layer. It intercepts, evaluates, and actively mutates the lifecycle of every incoming request. To see exactly how this works, we can track the lifecycle of a single JSON payload from a food delivery app as it travels through the gateway's pipeline. The API gateway acts as the absolute authority at the network edge, turning a chaotic mesh of direct connections into a highly secure, orchestrated pipeline. This diagram shows the gateway's internal pipeline, starting when a user taps Place Order, generating a JSON payload. Inside are key value pairs: user ID, restaurant, address, payment, and auth token. In Step 1, Request Reception, the gateway receives this payload as the single entry point. It immediately moves to Step 2, Request Validation. Before routing anything, the gateway inspects the payload to ensure all required parameters are present and that the data format strictly matches the expected JSON schema. Malformed or missing data is rejected instantly. Backend servers never waste compute cycles processing an invalid API call. Next is Step 3, Authentication and Authorization. The gateway extracts the JSON web token, checking it against an identity provider to confirm the user's identity and permissions. If invalid, the gateway kills the request here, bouncing a 401 unauthorized error back to the client. By handling validation and authentication at the extreme edge, the gateway ensures the backend services operate in a zero-trust environment. Every incoming packet is mathematically pre-verified. Even verified users threaten stability. Whether it's a malicious distributed denial of service attack or an accidental loop, raw volume can quickly overwhelm a server. The defense against this is Step 4, Rate Limiting. The gateway actively controls the frequency of requests any single client can make within a given timeframe. It tracks frequency using a Redis counter. If capped at 10 requests per minute, every payload ticks the counter up. Hitting the maximum threshold drops a physical block on their connection. Subsequent requests shatter at the edge, returning a 429 error. Once the 1-minute window expires, the lock lifts automatically, allowing legitimate traffic to resume without any human intervention. Rate limiting acts as a system-wide blast shield. It enforces fair resource allocation and ensures stability long before volatile traffic spikes can touch fragile backend databases. Client applications and backend microservices rarely speak the exact same data dialect. To bridge this gap, the gateway executes Step 5, Request Transformation, actively mutating the structure of the incoming data. The mobile app sends the delivery address as plain text, but the delivery microservice requires GPS coordinates. The gateway pauses routing, queries an external geocoding API, and injects the returned latitude and longitude directly into the payload before moving it forward. Active request transformation perfectly decouples client data structures from backend schema requirements. Development teams can upgrade their front ends and back ends entirely independently. The payload is now validated, authenticated, and transformed. It is ready for the backend. Processing this order requires coordinating multiple distinct services, creating the order record, checking restaurant inventory, and processing the payment. Step 6 is request routing. The gateway references a dynamic service registry map to locate active backends. Because microservices constantly scale, service discovery allows the gateway to instantly map the payload to the exact current locations of the active servers. It uses load balancing algorithms, like round-robin or least connections, to distribute this traffic evenly, preventing any single server instance from being overwhelmed. But backend failures are inevitable. An inventory service instance might suddenly crash right in the middle of processing the request. The gateway defends against persistent failures using circuit breaking. Detecting HTTP 500 errors or timeout delays from a localized failure, it physically flips a switch, severing the connection. Traffic is instantly rerouted to a healthy inventory instance, allowing successful delivery. Circuit breaking prevents localized server failures from cascading across the network. It isolates the damage and maintains high availability for the overall system. Once the backend services finish processing the order, they send their data back toward the client, triggering Step 7, response handling. The gateway intercepts the varied responses from the distinct microservices and transforms them back into a single, cohesive format the client application can easily read. The gateway optimizes future performance using caching. If the payload contains frequently accessed data, like a menu, the gateway diverts a copy to local storage. When the next user requests that menu, the gateway immediately bounces the cached data back. The request never reaches the backend. The gateway standardizes the final output and ruthlessly eliminates latency just as strictly as it manages the initial input. Zooming out, the macro-level impact of routing every single request through one centralized choke point becomes clear. Because the gateway sees every packet entering and leaving the system, it executes Step 8, logging and monitoring, serving as the ultimate source of truth for system behavior. It records detailed metrics for every payload's journey, capturing request rates, precise routing paths, exact source IPs, and exact latency timings. This telemetry data is continuously pumped into monitoring dashboards like Grafana or Prometheus, allowing system administrators to detect anomalies and troubleshoot issues in real time. By absorbing the brutal operational complexities of the network edge, the API gateway empowers client applications to remain lightweight and allows backend microservices to focus strictly on what matters most: core business logic.